Good morning. We're starting class right here at 8 o'clock on the 21st of September. The weather has changed for at least a few days. It's now cool and windy out. Finally, I mean, I'll take it. Yesterday was a really hot day, I thought. We're going to finish off Chapter 2, the Fourier analysis, probably look a little bit more at difference equations. I'm going to talk about some more hints for the problems. And later in the morning, after the lecture's over, for those of you that are in the lab, you'll see they've already got running on my tablet, Kyle, the IDE for working with the embedded system board for doing the real-time DSP, and I'll be demoing that in the lab time. So I'll start by just talking a little bit about what I've changed on the website or what's new. I see I didn't spell histogram correctly. I left an O out of that, but I did give homework papers back on Monday. It was challenging to grade through the papers. I'll be honest with you. This is my last semester, and I can honestly say grading papers is one of the least liked parts of the job. It's always been that way. It hasn't gotten any better. It's probably gotten worse in my feelings about it. Not because I don't like the work you do. It's because it's a tedious process to grade papers. And a lot of faculty shirk that because they have graders, because they teach larger classes. By and large, I never get a grader. And even one faculty member, who I won't name, who I respect a lot, he'd rather grade his own papers because he wants to see what's going on. And if you get a student grader, frequently they don't even know what's going on very well, and they don't mark very carefully. It's one of the things, and that's the way I graded, so I'm just giving a little spiel on that. I'm looking to make you better, and even if you did really, really good, I'm still going to pick on things because I want you to just know little nuances and things that I'm looking for, and this is part of the process. It's part of getting your money's worth, in my opinion. You want that. I used to have professors that graded my homework, probably when I took this class out of the Oppenheim and Schaefer book, long time ago. And he was a very picky guy. He was actually on my dissertation committee, and he had a dry sense of humor like a lot of us engineers do. And I remember I was in the graduate office. This is my weird story for the day. I was in the graduate office working late at night, as most graduate students did. I lived in a trailer park just north of town in Rolla, Missouri, and so I didn't really like my place very well. It was just a place to sleep. The furnace didn't work very well. It was cold. It was windy. Thought the trailer would blow over it a few times. If you've ever lived in a mobile home, as my landlord called it, because he grew up in the South, it's not the greatest to live in, but has anybody ever done that? Had to live in a trailer, mobile home, as they call them? It's different. I mean, it's definitely different. At any rate, though, one night I'm sitting there working, and I knew he was reading the first draft of my dissertation, and his graduate students were in the same alley of this bullpen area that we had our offices in. And he's there really late at night. I hear him enter the office from the far corner, hear him shuffling in, and he comes around the corner, and I'm behind a partition, so he didn't know I was there. But his students were there, and I hear this wham. He had thrown my dissertation draft from a distance towards a garbage can, and it landed in the garbage can, and it made this, really big sound. And he muttered something about reading Wickert's dissertation and how there's problems with it. And at that point, I went like this, out behind from the partition, so he could see that I was there, and he was reaching down at the garbage can. His face was bright red. I won't remember the exact details, but he was a little bit embarrassed that he had done that. But nobody's ever done something like that before, right? Stick your foot in your mouth and kind of like, whoops, I shouldn't have said all that. He had me fix some things, but at any rate. So I posted a histogram, and that's also up in Slack. This is PhD student that's conversing with me on stuff that I've told them I'm now in class. But if you go look in Modern DSP, I posted a link after I posted it on the website. So because I put a link in here in the channel for Modern DSP, the histogram's right there. So I can actually go look at it right here. I go look at it on the website. But my plan is to do this, and this was done in Julia. It was actually done in a Pluto notebook, but just put the scores in and do a histogram, and I'll do that for every assignment. And I'll eventually have composite histograms like this so you can see what's going on. It's not the same thing that you get if I was using, what's it called again, the CMS that we have, course management system. It's Canvas. Yeah, it's been Blackboard, it's been all these other names I can never remember, but Canvas would have a spreadsheet and then I could program it to do all this stuff. I have a spreadsheet that I keep all the records in, and that's where this data comes from. I load it into the spreadsheet, my spreadsheet, and then I just will do some work with the data. So if you ever want an update or status, I mean, I'll have the running total. You can just send me a message on Slack. So where did I end up, and so on and so forth. This case, no issue, right? Because one paper, one set of grades, everybody knows where they are on the histogram. But that'll eventually unfold in more detail. So are you seeing my broadcasts, I guess? Because when I do @channel, it lets me know that anybody that's subscribed to this channel in Slack is going to get an alert that this message was sent. Does that happen? Okay. It always warns me, and you can do these things on this channel too. You can put a message up, you can share something for anybody. And if you do an @channel where instead of an @name or something like that, I mean, is just the tagging that's part of this environment. So if I do the you can see here's all the names that are in the channel right now. I've tried to clean it up, get rid of some people that aren't around anymore, but it will warn you that some people that have been in my classes and are now in other parts of the country or drop the class, it will say, do you realize you're sending messages to 3 time zones? So what? I mean, if they're subscribing to it and they're probably not ever on Slack anymore, but it just, that's the way it works. But if you want to send a private message, of course, you can use the direct messaging setup over here. What else did I do? I didn't really do anything else. I had a question about the password, but I think you all know that the password is, it's there in Slack. I was probably just looking at it. And I don't share it on the video because I just don't want to make it too obvious for people that watch the videos around the world that they can get the solutions from the book, which are embedded in some of my solutions. I'm just trying to maintain integrity on that. So moving onward, I'm going to kind of go through a little bit of a tour of certain things, but I'm going to start with one of the last things that we looked at in terms of detail. We were looking at the moving average filter, and we were looking at the frequency response of the moving average filter in the general case of a non-causal filter, which has M1 taps in the impulse response for n less than 0. Of course, it has a tap at 0. That's the present value that's going to get a weight. And then it's got M2 taps in the past that it's going to form into that moving average. And when we work that around, and I didn't give you the intimate details, I told you that the general form of the response, there's a linear phase term up in here. Just remembered I didn't pull out my pen yet. And then there's the sinc function, or the alias sinc function, sine mx over sine x is what's in there. So this piece right here, so I can get my pen to start working. So that doesn't contribute to the magnitude response, it only contributes to the phase response. And then the sine mx over sine x type function is what this thing is right in here. And then a plot for particular values shown down below here. But I had told you that it's also in a Jupyter notebook, Jupyter Lab notebook. And if some of you are still using Jupyter Notebook rather than Jupyter Lab, I highly recommend you change, because the notebook itself is very, very old. It doesn't have a lot of features. And I don't think it's as secure either, but Jupyter Lab is what I'm having you launch. And I just noticed at least one, maybe two people were using the old Jupyter Notebook, which they just can't shake the word notebook off of it because that was the name they gave it when they wrote it. But that's dates back to about 2015 or so, I think, in that neighborhood. It was like the pioneering web-based environment for programming in Python. Julia at that time was much in its infancy, and then other languages. So I just thought I'd jump over here, though, and do a little bit of looking. Well, I guess I'm going to do two bits of looking. I'm going to show you how you can model this directly without worrying about singularities. And then I thought I would bounce way back up here to an example we did a long time ago, but I just wanted to give a lesson on Python programming. And that's way up here. That was example 2.4, where we were convolving a pulse with an exponential. And it's not on the details of that, but what it is on, it's on so what I want to do is just go through how you would write a piecewise continuous function. And I've done this in some of the examples for both Julia and Python. I put out so much stuff, I just put it out there because I wanted to have you have the ability to go grab something and look at it and have a lot of different options, but I'm going to just drill into modeling this in Python. So we'll look at that first in Python. So that's what's right over here, example 2.4, and this is the notebook. Go back to the web page here for a second. This is the notebook that I posted after class last Wednesday. So if I go into tutorial notebooks for chapter 2, I reposted a notebook at 1:48. I guess I did it on Thursday because I added more stuff to it. And then I also put in a PDF rendering of it so you can just look at it directly without having to download it and bring it up into Jupyter Lab. But this is a whole array of stuff from chapter 2, things that could be resources for any of the homework problems, in fact. And I'm actually going to add a little bit more to it today. But at any rate, let's just consider plotting this, or creating a function to plot it. This would be what I would call an analytical closed-form solution to this convolution. It produces the picture below, but if we want to have a function, what we want is a function in code that's going to return the functional values if we put in an index n, and we want to write it such that it can take an array of indices, whether it be Python in this case or Julia. So in Python it would be the ND array, the n-dimensional array structure that NumPy, the package that we use most frequently for numerics in Python, supports. So I probably should, I can't slide that over anymore. Is that big enough, or should I zoom in one level? Is it okay? Okay. So I just wanted to write a function, and in Python you start with def, which means you're writing a function. If it's Julia, you start with function, and the syntax is kind of like in MATLAB. You start with the name function, and then at the very end of the function, you have to have an end. I don't know if that is still sitting strongly in your brain from your MATLAB training. Python doesn't do it that way. Python is a language that, unlike Julia and MATLAB, it's sensitive to spacing, horizontal spacing. So the general rule is you have an editor, and the editor doesn't use tabs, but it uses spaces. And you can control that, but Jupyter Lab is already set up to abide by the standard. So you can see it's going to just shift over. But no, I'm hitting the tab key to do that, but then I'm using the arrow keys, and if it was a tab, I wouldn't see any spaces. It would just jump right back to the 0 position. In Python, though, that's not a good thing. Tab characters in Python code can cause problems. So the editor is set up to put in a four spaces when you hit the tab key, but it's not putting a tab into the document. Why am I making a big deal out of that? Because when I was first learning Python, I was so aggravated by this fact. I was getting caught by it over and over again. And the interpreter in Python flags things like that. It says you have improperly spaces in the line. So more on that in a second. In Python, you use these triple quotes to put in a block comment. And by tradition, the block comment always follows the function definition, which in this case is just going to take a bunch of input variables. In this case, it takes 3 variables. Unlike MATLAB and Julia, you don't indicate what's being returned from this function until you get to the end of the function itself, and that's where you put your return in. So frequently, what I do in my docstring information, I will put in an actual example of how I'm going to use the function. It's going to be y equals pulse response something or another, just so that I know what the output return values are. Otherwise, you have to look to the bottom and see that. So in this case, because I've already compiled the function, if I go Shift-Tab on the function, right now with the cursor sitting inside the parentheses, you can see the docstring is right there. That's between the triple quotes. And I can see the signature is that, but I can also see clearly with my second line in my docstring that it's returning one array value, or it could be a scalar, but in this case I know it's going to be an array value. When you start using Python more and more, Julia has these same issues. If you don't separate out the variables, what happens is everything gets crammed into a single return variable, and then you've got kind of a mess. You've got more stuff in there than you want. You have to parse it back out again. So it's best to, if it's 2 variables going to get returned, separate them, y and comma n equals or something like that. At any rate, so just like in MATLAB and in Julia and in Python too, I like to pre-allocate so that I'm not trying to do something with an array that's expanding in size every time I go around a for loop, because that's inefficient. So I just pre-allocate an array of zeros, and if we were not importing all of NumPy, we'd have to put np dot out in front of that. But again, Shift-Tab, just check and see what type of arguments you can put into that. len is just going to be the length of n, so it's going to take my index array n, and it's going to create an array of zeros that match it. And then I start a looping structure, which is one of the most popular looping structures within Python. Python has while loops as well, but for loops are probably the most common. And you can for just on an index and use the range statement. So I put that over here, saying you could just do for k in range length n, and if I was using the range statement, it would just simply count from 0 up to the length of n minus 1, and it would give me that as an iterator for values of k that would be used inside the for loop. but one of the most efficient ways and useful ways and most powerful tricks to learn about Python is you can use enumerate. Julia has an enumerate type method too. What's powerful about it is if I enumerate over the index n or whatever I'm enumerating, I get two things back from it. I get the index corresponding to the iteration itself, and then I get the value held at that particular index. So in this case, I'm saying I'm going to do k, which is going to be the index, which will start at 0, because that's where arrays start in Python, and nk is going to be the values held at each of those indices. And both of those turn out to be useful in doing this piecewise function. I need to know what the index of the array is so that I can push things back in to y at the appropriate index. So I need a way of pushing things back in. But then I'd also like to know what the values are held in that array n, because that array n might start at -20. So at index 0, I get a value of -20. I don't get 0. So you're totally freewheeling at that point. You can be very flexible. So then this set of if, elif, and else is building out exactly this piecewise function. So I say if nk, the value of held at index, at the very first index I iterate with, which is k, I just say if I'm seeing nk come out of this enumerate and it's less than 0, I know that I'm in the region where y sub k has to be set equal to 0. So and then I'm using this k, which comes out from the enumerate, just to properly point into the array. And then the next statement is elif, and I put a comment in here saying that I could make this more emphatic. So if I uncommented that with control / I could replace that and take that away. And what Python has for logical statements, it's very easy. It's probably the easiest language to write logical statements in, because you don't have to use double ampersand or pipes or whatever like you think of in C, where you're having to do and or logic. In Python, you get to write out the word and or very clearly. So here I'm saying two conditions. This if is going to fire if nk is greater than or equal to 0 and nk is less than or equal to n minus 1. But logically, I don't need that in this case. Why? The very first case I test is nk less than 0. So if I pass through here, I know that I'm at nk greater than or equal to 0, right, logically in the program. So I just need to see also if nk is less than or equal to n minus 1, because I know I've already cleared the first hurdle. Even it may not be less than that. Logically, it's going to fall into this next case. So then I just write out the expression. And here I'm just writing out that case. And I'm using the syntax of Python, the double asterisk for power. And numerical Python is very lazy. You don't have to put a dot anywhere in here. It knows that I can take a scalar to a power, and it'll just do it pointwise. In this case, it's not doing it. It's not using an array, though. It's just putting in a single value, and I'm going to set it to nk plus 1, and that's exactly, n plus 1, and then divide by 1 minus a, and then poke that into y at index k. And then the final case is the catch-all, the else statement, always a colon to begin that, and then there's an indent, and that occurs automatically. That's what's required. And then here's the tricky part about Python. The very last case, I don't have to outdent and put an end or anything like that. What Python senses is if this last case has this indent and then nothing follows it except for a statement that's outdented, it just automatically is assuming that I'm done with the if statement. So the if statement is like that, and it seems incomplete if you're like learning this from another language, which I was. I programmed in MATLAB and in C, and I thought something was missing. If you do this in Julia, though, you do need to have an end statement, so it's more like in MATLAB. But it's the fact that it outdents. I could do this, and it's just fine because there's nothing on that line, but I can be tight like that and just say, I'm done. So Shift-Enter, and it builds it or compiles it. And now I can go ahead and use it. In this case, I ran a collection of values for different values of A and N, just to also demonstrate how you can use subplots very much like in MATLAB. So I create all the pulse responses here, then I create an initial figure, and what I'm doing here is just creating a size for that figure. So I'm saying 6 by 5 inches. There's lots of arguments that can go in if I do Shift-Tab, what you could do with the figure function itself, and this is part of matplotlib.pylab. But I'm just saying 6 by 5, and then I'm going to create a subplot, and this works exactly the same way it does in MATLAB. It says I'm going to have 4 rows and 1 column, and then the third argument is which plot I'm going to be addressing. So if it's an array of plots, it starts in the upper left and then goes across and then down the next row, down the next row. So if I had like 5 by 5 plots, this index would just keep growing from 1 up to the number of plots in the array. In this case, there's only 4 plots, so my index at the end there just goes up to 4. But remember, MATLAB did it this way too. Julia is different. Julia, you have to use a plot layout, and I'm not going to discuss that, but it is definitely different. There's probably other tricks in Julia that I haven't learned to do a layout with, but subplot, as far as I can tell, I haven't found it. So there's my array of plots. And then in this particular case, I decided to just convolve directly using the function that I created, convolve sum. I know this won't be as precise because this is not a closed form analytical expression. This is just convolving a finite length sequence times the impulse response, and I'm just going to slide it past. And if I don't include enough values, I might get some I might get values that aren't totally correct. I might get some artifacts if I'm not careful with this extent variable. So I plot that, and then that's down here. And then a third technique that we all have already seen, that if we understood later that a first order difference equation could be used to model the pulse going through an exponential decay. This turns around the original example problem, but it's still a rectangle and an exponential decaying pulse. So I just set this up using L-filter and put in the coefficients, and here I'm using minus 0.6. In this example, when I did the convolution sum, coefficient is 0.6, and on the original pulse response up here, I did do one example where it was 0.6 and 10. So now I'm going to leave the discussion of the programming and talk about something else just briefly. Any questions, though, on the programming aspects of Python? Like I said, Julia would be very similar. I'm spending a lot of time myself learning more about Julia because I think that's where I'm going with my next job. I mean, I'm wanting to figure stuff like that out. I want you to be comfortable with what you're doing, and if you think Python is where you want to be right now, I definitely stay with Python. But I may ask you to try something in the first project with Julia if we don't do C++. I mean, we're in school, so we should be able to jump around and kind of look at different avenues. If you're working for a company, they might dictate, you got to use MATLAB, got to use Python, and probably they won't say use Julia right now, but I'm just kind of forecasting, and I want the speed, but I'm on a project, a new project that the Army's funding that's kicking off tomorrow, and I notice how many people are on the invite. It's like the whole company, and they might lay down some rules to say all development, any prototypes, anything that we do, we have to do it in Python. I don't know what's going to happen, but I'll play by the rules, at least on my deliveries to the team. And you guys, in your work, in this class, you can do whatever you want to do, but when you work for a company, you do have to play by the rules usually. I say usually because if you think you can get something done faster, I take speed over teamwork if I know I'm going to get beat up later for not having it done fast enough, right? If you know you can get done faster, I can explain myself later, but I can't make up for lack of results if that happens to be the case. So any questions on this basic function? You will be having to do programming specifically of functions in the first project, and that's a ways off. How far off is it, you're going to say? I like to see it you're going to formally get it assigned in October, and it will be due before Thanksgiving is my plan. That's usually the way I do it. This is going to be the project that uses Pi Audio Helper to do real-time DSP and Jupyter Lab with widgets, and possibly the C++ like I did last year, but I might replace that with Julia and benchmarking. So the old project is up there, but I probably will change it in some way. Certain parts of it are going to stay unchanged. So another thing that I decided to do, because it's something I did in my solutions for problem set number 2, is sometimes you like to compare data from a closed form solution, like you solve a difference equation using the classical technique and you get some expression that you can just do like we were doing over here, and I'm going to dial down to that well, I'm going to dial down, I could dial down to a similar example, but I'll just, I guess, stay on this for a moment. You get some expression that might have u of n's in it and has different exponential terms. Let's just go down here anyway. Might be an expression kind of like this, and this is closer to home, case in point, for the homework, but I'm not going to work the homework here because that would be working your problem, so I'm not going to do that. But it might be a solution like this, and you know from the difference equation that you could just crank this difference equation by plugging the coefficients into L filter and driving the input of L filter with the appropriate x values. I guess you got to go up here. And just getting the numerical answers out. And you'd like to see, is my closed form solution gotten through the classical solution technique in agreement? And plotting pictures sometimes is very, very good. I mean, there's two things you can do when you plot pictures. Number one is you can plot one waveform right over the other, but a stem plot doesn't work really well. You can put it in a stack of 2 plots. Or probably you'd say, I don't want to do that. I'm going to take the difference between one technique and the other and see that I get 0. That's probably the best way. But looking at a plot of all zeros is kind of hard to explain to me, like, look, it's 0. That's what I wanted. And then I don't expect an answer of 0, but if I know it's the difference. But another nice technique for me, I think, is to create a table where you're going to look at n is equal to 0, I get this from one formulation, the closed form I get this, and then just compare. So within Python and of course Julia, I should stop saying this because Julia is following Python, right? Python is first, so. But there's a popular package out there called Pandas. I forget why it's called that. All I know is a guy at the New York Times in New York is the creator of this package. When I was at the SciPy conference, and I'm wearing one of my SciPy shirts that I got, the Anaconda shirt, he wrote about how he created this package for what he called data wrangling. Has anybody ever heard that term before? How about data science? You've heard that term before, right? Machine learning. I mean, all these things kind of followed in suit, but the idea of data wrangling is kind of the essence of the Pandas package, but Pandas itself is used by data scientists and machine learning people everywhere. It's probably one of the most popular packages in the data science community. So first off, how did I get it in my system? So here I'm running my environment to support the notebooks. In this window, it just so happens I'm running a Pluto notebook, but I just opened up another Windows shell and I launched Julia, and then I imported Conda, and then I just said I'm going to add a package that we didn't put in earlier. I'm going to do conda.add pandas. I'm just sort of reviewing how you can add things or remove packages within Conda, in your Conda environment that's inside of Julia. So it went off and it went off and did some things, and it said solving the environment. That's one of the things. My shirt says it's from the people that created Anaconda. Figures out the environment. It figures out what it's going to have to do to add that to this particular Python environment so that it plays properly and doesn't create an issue. I don't talk about this enough, but one of the things about any of this open source software is when you put a bunch of different packages in, written by different authors, there is always the danger that there will be some incompatibility. And so you'll add a package, and then all of a sudden your Python environment is not running properly anymore. Something kind of gets broken because a package goes in that is too new or too old or does something to the environment. And that's what Conda is there, and pip, the package manager, native for Python, is supposed to do that too, but humans created these things, and humans make errors, right? So there's so many different variations of packages that somebody could put in their environment, and there's always a slim chance that something will blow up. Then you have to start over again, building up your packages and your environment. But Conda works hard, and that's why it gives you these messages. It says it's working hard. It figured out what this environment needs. It sees what packages are in there, and it sees to add the package pandas. It's going to have to pull certain versions from Conda Forge, which we set up earlier as the cloud repository for new Python packages to put in our environment. It actually puts in a couple of other things along the way. It put in 3 things. And then it proceeds to do that, and eventually you see it cranking along like this, and then when it was done, it was done. And so I didn't have to shut down this version of Python over here that I'm running in. I just had to add another package to it, and then I could go up to the top of my notebook, and I just simply added one more line in up here, import pandas as PD, just its short name that the community, the data scientists in particular, if they're going to use pandas, they always give it the short name PD. Just like I use signal for scipy.signal and so on and so forth. Most people would import NumPy as NP and import matplotlib pyplot as PLT. I'm cheating here because I'm making the environment more friendly like MATLAB would be, just have everything already loaded inside. You might have a coding standard in your work though that says no, you can't do that. But this is a learning environment, so I think it's okay. So As soon as Pandas was installed, I could back away from this, just put a period, I could hit tab, and I could see all the myriad of things, methods and functions, classes, all this stuff that this guy that started this about 6 years ago, how it's grown bigger and bigger. I took a class on Pandas when I was at the SciPy 1 year. I don't remember a lot of it, but I was in a class for 4 hours. I wanted to do something very simple with Pandas, so I didn't want to get carried away. So what I did is I said, let's just use a method called data frame, and then I'm going to create a dictionary, and that's another data structure that's inherent to Python, the dictionary. And the idea of the dictionary is you have a label that goes with some piece of information. It could be a string, it could be an array, it could be a scalar, and so on and so forth. So this is just one of the so-called constructors that's available for creating a Pandas data frame. So inside the curly braces, I'm creating 3 dictionary inputs. One has a tag name of n index, and I'm going to put the integer array n. And that's what the colon does, and then a comma, and then another tab, another string, y theory, y convolution sum, and y linear constant coefficient difference equation. So on the fly here, I used the function we created earlier and just created it with a pulse width of 10 and exponential decay of 0.6 to create the array corresponding to these different tags. And then the only thing I'm after, I don't want to wrangle data like people would normally do with Pandas, do statistics, other plotting things. I just simply want to use its table formatting capabilities. So I'm using something pretty minor, but it does organize, and this will produce a table which will render out through Markdown and will look pretty nice. So I just simply wanted to plot 0 to 9, the rows 0 through 9 out of this array, and I could plot more or less, but I'm plotting 0 through 10. And when I do that, I have an error because what did I do? I probably didn't run some line up here. I might have left this in a funky state, so I should have not done that, because now I'm probably going to pay the price for something not working right. Some variable is not setting right. Let's just try this again. All arrays must be the same length, so I changed the length of something inside of here for creating this table. It wants to create, I want it to create a data frame that has the same number of rows in each of the columns. So I must have something that's not right here. I've got n, n. These two over here are probably suspicious. So how am I going to debug that? I'm going to do something. I'm going to terminate this, put a parenthesis there, and then make that a comment. Okay. Why did I do that? I mean, this is another little, I'm going off axis a lot today, but I'm just trying to show you how my mind works and how I want you to be able to blast your way through coding as well as analysis and not get frustrated. So I saw the error message saying the number of elements aren't the same. So this one I know has a length corresponding to n, and that is the same n. So one of these two guys is got a different range associated with it right now, for whatever reason. So is it both of them or is it all of them? So I'm going to now bring back in the next one. And I'm going to attempt to close it off again and then comment that one. Okay, so the convolution sum is the one that's messed up. For expediency, what I'm going to do is I'm going to delete that one, and I'm just going to move over to the LCCDE and use that one instead, and not include the extra one. But it must be created, let's see. This y here must not have the same number of elements in it. Okay, I reran the LCCDE example up here, which got the new y from an n, and the n was defined earlier up the page, so now it's consistent. And this could be exactly, the convolution sum result I threw in as a bonus, but it doesn't need to be here. This could be exactly what you're doing in the homework. You're going to get a solution by driving the difference equation just as a check, but then you want to compare it to your analytical solution, which might be something like this. So that's what I'm doing right here. The theoretical or closed form solution is giving me these values, and my n index just tells me what my n value is. So starting at 0 and then going on up. I think what was messing me up is this started at -2, and the convolution sum expression started at 0. So I changed something late last night when I was reworking this. But the idea is you can say, look at this table, look at my closed form solution matches the simulation, and I'm good to go. Get the idea? I'm just trying to provide a means where you can just check your work and see what's going on there. So now I'm using the index, which is this tab over here. That's the file view. That's the table of contents. So I'm going to drop down here and talk about the alias sync function. So that was the other thing we were doing here before I go back into some examples. So if I wanted to plot this function, how could I do it? I could write this out as sine over sine, but the problem is I know there's going to be a singularity in the denominator, and what happens when you hit a 0 in the denominator? You get a warning, right, or a serious error message. It's like you've got a not a number, or an infinity case. So there must be a better way to handle that. We know the sync function is sine x over x, and that has a singularity at 0, but that's been patched up in the definition of sync, or sine x over x. So can we do that? And here in the notebook I just say, look, there's the definition of sync. I can expand sine omega m over 2 as sine omega m over 2 divided by omega m over 2. So I'm just throwing, I can't write on this because it's in the notebook, I'm throwing in an extra denominator term as if to say if I wanted to create a sync function, I would put that in the denominator, and then I have the sine omega over 2 in the denominator, and I'll put an omega m over 2 in the numerator, and then I'm left over with an extra m. And what I've done is I've got in this first term, I've got a sync function, which is this guy, and then here I've got a sync function in the denominator if I pull the m out. So now I've written the alias sync function is a ratio of 2 sync functions, and I know this is robust because sync handles its singularity properly from a numerical standpoint. All of you will deal with this sometime in your life if you haven't already, and that is trying to figure out how to make a function not cause a blow up when it hits a point of singularity. Is anybody, I'm just curious, when you took your C programming class, did you ever have to do something like that, where you actually had to patch things up? I call it patching up a function. I mean, how do we know about how to handle the singularity in the sync function? It's something you learned in calculus. Remember when you take a limit of something and you don't get the proper limiting value unless you use blank rule. Yeah, exactly. So that's how we figure out how to patch this function up, is L'Hopital's rule, or something similar to that. So you know that the limit as the argument goes to 0 doesn't go to 1 over 0. Instead, it becomes just 1. Remember that? So you do use calculus a lot. Why do I say that? Because I'm writing code in C++ a lot for what I'm doing in this job, and you've got to manage things. Things will blow up on you. When you're in an environment like Python, most everything's managed for you, and you don't have to get all freaked out because it doesn't blow up that often. But in the kind of outside the box, things will be a little bit testy, and you have to just go study that and take care of it, manage those special cases, so the numerics can work properly. Calculus still rules in a lot of what we do. So here's the alias sync function, and I can now just run that guy, and then if I wanted to increase it, say make that go up to 10. So this would be omega equaling 0, and this is omega equaling 2 pi. And the way I always know what m is in here is I count the number of humps. So starting at DC, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that tells me what m is. So if I was to make this be 7, let's say, I can check that out again. 1, 2, 3, 4, 5, 6, 7. And you might say that looks like one hump because it's wrapping around, but that's just what the rule is. If you want to just count the number of humps between 0 and 1 less than the beginning of the repeat, then you have to add 1 onto your number. And if I put this at an even number, like at 4, there's not going to be a hump at pi over 2. There's going to be a 0 there. This is the moving average filter, and this is also known as a comb function because it has the humps and the zeros in it, and that's usually referred to in signal processing as a comb-like function, like it can comb your hair and comb through and wipe things out. Okay, I'm ready to go back to the notes finally. But if you've got questions on all the coding and Python stuff I was talking about, ask away. I don't want you to be too confused. I say too confused because you are going to get confused. The best way to unconfuse yourself is to sit down there and fumble around a little bit until you can convince yourself, yes, it's good. And now I'll just jump back for a second. What do I very frequently do when I'm coding? If I just define this function up here, I will do things like test cases. So I might add a cell above here. And if I was writing out this function right in here, I might, if something was not working right, I might do something like this just as I'm getting started. And I might see what happens when I put w equals 0 into this function and see what I get. I get 4. Is that correct? Remember, m is equal to 4 up here, so I could just paste that in up above if I wanted to, just so I'd have it all in one cell. So I get 4. Then I might put in 5. See that I get 5, and of course the picture here I can see the amplitudes are changing, but you might just look at the code and see I have a sync function divided by a sync function. So I might look at, what is sync of 0? It's 1. That's where L'Hopital's rule was used to patch that up. So these two functions both give 1, but the m out here, that's where the 5 or m is coming from. So at that point, you're supposed to go, to yourself, thumbs up, it's working correctly. This is what I'm expecting to see happen. And then right after I do that and right after I'm comfortable, I will clean up my mess maybe and trash these cells if I'm going to turn this in or post it for you guys. It's called my scribbling pad. I mean, I just go create a cell and scribble a little bit and kind of validate something. Still, though, in the notebook, you can cordon that off and put some notes around it and said I was experimenting, and then do some more work. Something blows up in your face, and it's like, I thought I'd resolved that issue. What was I looking at before? Do another little experiment and see if you can fix it again or look at what's still going wrong. I did a lot of that yesterday on something I was working on. I was trying to figure something out. Was it my C++ code or was it my Julia code? And I was, sending stuff from C++ over into Julia and plotting it there, because I'm delivering C++ code, but I'm evaluating and testing it by doing plots and things in this case it was Julia, it could have been Python. So now what I want to do is go back and review some things that are in the homework and kind of smooth some things out. So I want to jump back as far as I think I need to, and then kind of come forward and smooth through things I skimmed through last week. So my first plan, or my first thought, is what to do on problem 9a, which has got a number of parts to it. So what I'd like to do is just jump back to an example that we were looking at earlier. And it's an example that well, there's two examples I refer to in the hints for problem 9a. I refer to example 2.9 and also to 2.10. So 2.9 is I think I might have that written down wrong. I think I meant for that to be 2.10 and 2.11, but I'm not positive. I'm going to have to change that. But I wanted it to, one of these I wanted it to be a second order system. So 2.10 is first order, 2.11 is second order. So this is really the one that I wanted. So the hints page should say example 2.10 and 2.11. So I wanted to take a look at how to solve by classical means the difference equation for any type of input. In this case, it's the delta function input, but what you have to do also in problem 2.9a is do the step response. So you're going to do this problem, this type of calculation a second time with x of n equaling u of n. And then you'll have to use the method of undetermined coefficients. So where does everybody feel about this? Do you want to see more discussion on this? I could use this as my starting point if I wanted to. Here's the impulse response. If you wanted to get the step response using the classical technique, you'd have to change this problem around and set x of n equal to u of n, and then you'd be solving the homogeneous equation first, and then you'd be adding in the particular solution by assuming a form B, and then you'd use this example for the first order, extend it to the second order, where you'd be doing this sort of thing, solving for what that would be. I'm just saying, do you want some more detail looking at that, or do you want me to just move on and say it's in the notes? You can extend the notes, or pardon me?
I would take the detail.
Okay. So what I'm going to do then is I'm just going to take this example and use it. So what I have to do is I have to get it out of here. So just wanted to put that on my clipboard, and now what I'm going to do is I'm going to go create a blank document, put about 10 pages into it again. See why it won't paste in there. Where did it go? I thought it would show up in here. Oh, there it is. Ended up way down there. Okay. I guess I made a copy of it, or this thing's not. Okay. I just wanted to have a starting point. So I'm just going to use this as an example that's related to 29A's request to find the step response. Now you can find the step response from the impulse response and then accumulating it. I talked about that last week, but suppose you wanted to follow the technique. Let's see, get to the right page. Suppose we wanted, too far away. Suppose I wanted to follow this approach. I would follow this approach to get the impulse response in 29A, where it says find the impulse response. I would then go to the classical solution technique. One approach of two that I like is to find the step response directly. So we would just go back and we would use the techniques of examples 10 and 11 to do that. So I'm going to pick up on the homogeneous response, which is just immediately jump into that. I'm wanting to get another screenshot, so I'm going to try to clean this up a little bit. Okay. So this is the homogeneous response, which we've already looked at. I guess I could make that smaller. I don't think it's going to let me edit it though. Yep. I'm not going to mess with it too much because I feel like I could lose it. So if I wanted to find the particular solution, I need to find the coefficient b. And then once I solve for b from the difference equation at the top, I will add that into this y of n. This is the homogeneous equation right here. And I'm just going to add that in, and then I'll solve for the remaining coefficients, a1 and a2. So the first thing to do when solving the particular solution is, remember, I take the difference equation at the top and I force into it. I make sure I choose a value of n where none of the terms vanish. So I'm just going to guide my way along by looking at my solution. See, we got impulse response, frequency response, step response. So I'm going to get the particular solution, and I'm going to choose n greater than or equal to 2. So if I do that, making the substitutions, I'm going to have and I'm just going to suppress n. So I'll have b minus 3b minus 4b equals my amplitude at the input is u of n, so the amplitude is 1, so I'll have 1 plus 2. So grouping all that stuff together, I have minus 3 minus 4 is minus 7, and then plus 1, so that's minus 6. Minus 6b, so I'm going to have b is equal to minus 1/2. So now I can write out the general solution. And I've never done this before for this difference equation, but it should work. This is an unstable difference equation, so that part about it is wonky, but I should still be able to have all the terms in here. There would be a u of n on here, but I'm just suppressing it because of that. So I know that that's in my solution, and now I just have to go ahead and go ahead to the original difference equation. I have 0 initial conditions, so when I'm solving the difference equation, I just want to put in all the terms, and what I have to do is I have to rewrite it here. So I have y of n equals 3 y of n minus 1 plus 4 y of n minus 2 plus x of n plus 2x of n minus 1. So I'm going to plug in n is equal to 0 down here, and then I'm also going to take my general solution and evaluate it at n is equal to 0. So on the left-hand side, I'm going to write what I get from my difference equation when n is equal to 0, and I have two terms that are going to be sitting at minus 1. So there's no output because I'm assuming 0 initial states, because we're not given any other information in this problem. We're doing the step response just like you would the impulse response. That's 0 initial conditions, kind of by definition. The system is at rest. So I could write the zeros out here, but I'm going to have 0 plus 0, and then top side here I've got y of n, which is, or x of n, which is just u of n, so that's going to be 1. And then the last term is u of n minus 1, so it hasn't turned on yet, so that's 0. And then for my general solution, just up above here, I've got a1 times minus 1 to the 0, so that's going to be just a1. And then a2, 4 to the n, that's the nasty unstable term, but we're going to just move it through here. That's going to be a2. And then I step myself forward, and I'm going to go at n is equal to 1. And now I'm going to have y. When I step n is equal to 1, I'm going to have y at 0. So what was my output at 0? It was 1. I got that from n is equal to 0. So I'm going to have 1 from that very first term in here. Well, I'm going to have 3. Never mind. Get that wrong. Then I go up to my difference equation again, and I've got 4 times y of minus 1, so that's still 0. And then I have, from the driving function, I have u of n. U at 1 is 1. And then 2 times u of 1 minus 1 is 0. That's also 1, but there's a 2 in there, so it's 2 times 1. And then going to my proposed solution over here, I'm just going to, oops, I realized I forgot something in here. There's a minus 1/2 up here that I forgot. Then I'm going to plug in n is equal to 1, so I'm going to get minus a1. And n is equal to 1 on 4 is going to be 4, so 4 a2 minus 1/2. So now I have to do a little bit of algebra to solve for a1 and a2. Am I making sense? Okay. So doing the algebra, I would take the first equation and I would bring the minus 1/2 to the other side, so I would have, and then switch them around, a1 plus a2 is 3/2, and then down below here I'd have 3 plus 1 plus 2, so I'd have 5, 6. 6 plus 1/2, I guess that would be 13/2. So I'd have minus a1 plus 4 a2 is equal to 6 and 1/2, 12, 13/2. Yeah. You're talking about right in here where that?
Is that now 3 2s for the y0?
Yeah, I think I made a mistake. You're saying I forgot the 1/2 in here.
Yeah, when you fixed it and then just down below the y0.
Yeah, let's get myself back on the right page here. No, I was getting the output was 1. This was the output of the difference equation. I just cranked it for n is equal to 0, and I got 0 plus 0, 1. So y at 0 is 1, okay? And that went in right here.
Yeah.
And then there's a 3 out in front of that, right?
Yeah.
The other term was still off, and both of the step functions in here are activated, so I get 1 and 2, and I get 3. So that was this piece. Good? So now what I would do, I'm just looking at the algebra, which is where you can obviously make mistakes. I'm looking at taking the two equations that I've now simplified, and I look at it as, let me just add these equations because conveniently the a's are going to cancel out. So now I'll have 5a2 5a2 is going to equal 13 plus 3, which is going to be 16 halves. 16 halves is 8. So a2 is going to be 8 over 5. I supposedly made 10 blank pages, and where did they go to? They didn't show up. Something got reset on here. I've only got one page to scribble on until I make some more. Okay, so I can now solve for a1. a1 is going to be 3 halves minus a2. Oops, I got a mistake in here. How did I end up? Oh, never mind. Okay, so 3 halves minus 8/5. So 15 minus 16 is minus 1, right? I'm just solving this, putting it over a common denominator, 3 halves, cross multiplying, so I have 15 minus 16, so I have minus 1, 1/10. So now I can plug back in my solution up here, and I can replace that by and then I can replace this by 8/5. Then I can put a u of n outside of all of that just so I could go off and model that. It's still going to go on stable though. It's not going to be a pretty solution, but it is going to have a minus 1/2 u of n is going to show up in there due to the forcing function. I just did this to carry out an example that was started in the notes. What you have to do is a different equation. The difference equation that you're solving though in that 9a is used all the way through 9a in the 3 parts of it. So the one you're doing is y of n is equal to minus 5/6 y of n minus 1, 1/6 y of n minus 2, and then equals 1/3 x of n minus 1. But applying this exact same technique to it. And as I said last week, you could circumvent what we just did. If this classical solution stuff just seems really grueling, and the reality is, as an engineer, you have grueling parts of your life, right? I certainly do. I mean, maybe it's mowing the lawn and pulling out some bad weeds. I don't like doing that either because I rip my hands apart. I still have a thumb that I messed up with the clippers 2 weeks ago. I really got into pulling out some elm trees, the wild elm trees that grow everywhere. They're nasty, right? They just keep coming back over and over again, and then I was chopping up the branches to put in the trash. Should not have gotten so aggressive because I hurt my finger. But at any rate, so there's some pain involved here too. If you don't like doing that though, we do have the option let me just try this again. So we have y of n This is the difference equation for that problem. Those are the three things you do in this problem. You find the frequency response, you find the impulse response, and you find y s of n. I did point out to you, though, that you can get the step response by accumulating the impulse response, because of the fact that when you accumulate a delta function, you get a step function. So this is a linear system idea where you're going to change the order of the operations. You're going to accumulate the impulse response rather than accumulating it on the input to convert it to a step and driving it through. You're going to drive a delta through the system and then accumulate that output to make it look like the step response. So this can be done too. This involves finite geometric series ideas, and it's a little bit messy too. I did them all because I wanted to just create confidence. I did the step response classical technique I just went through. I did it with this accumulation technique, and then I took and used L-filter in Python and just drove a step into it and verified that that gets me the same answer too, numerically, which is what you do in hardware that you'd ship to somebody. I mean, understand that this business of doing this analysis on paper and solving difference equations, doing Z-transform methods, doing Fourier methods, those are things that are just the backbone of digital signal processing. What gets implemented and shipped to somebody is generally going to be an algorithm running some filtering operation, and it's going to take signals from point A and deliver them to point B with some processing steps in between. So don't think that this analysis gets shipped unless it's in an appendix of a report or something, but that's part of the nature of engineering, right? You're grown up enough to understand that. I mean, the analysis, though, is part of the fun of getting there. I mean, that's where you get to be happy that you understand that it works on paper, you code it, and it works, and you're confident in that. Don't sell yourself short with your bachelor's or master's degree in EE. You're just not a technician that cranks things and doesn't understand what's going on. So you got this working from multiple directions. So I think I've handled that fairly well. What I'll do to provide continuity, this will be something I'll do later today, is I'll just finish working this out to just verify to me that, kind of like what I was doing in Python here, I will go back to this pandas, and I will just verify that a theoretical step response and one by cranking the difference equation for this unstable system does at least match. I mean, I know what's going to happen is these values are going to climb exponentially because of that 4 to the n that's in there, but I've still gotten the step response, and the numbers should still track from both solutions. Does that make sense in terms of the basic idea of just having a follow-through on it? I don't ask you to do that for the homework, but if you're wanting to validate your solution, it's a nice thing to do. I did a table compare. I'm going to modify my solution now to do it in pandas rather than just compare two arrays from Python. I did it for both the impulse response and the step response. So on purpose, you can't read this, but you can see my analysis is this blue box, And then down below here, I've got a code cell from Jupyter, and then both of these sets of code at the bottom. One is the theoretical from the difference equation hand solution, and the other one is through the LCCDE running through LFilter, and I just can see that the numbers match. Okay, it's about time to take a break, but I want to just kind of get back over to the notes now and just see where we last were. So I cleaned that up. The hints page needs to say examples 10 and 11, and that's kind of what I've already put into the lecture for the day. Talked about LFilter a lot, and you've been using it for a while now, so I don't really need to go through that in the notes. I don't care about zero initial conditions right now, but that is the very first project problem. You're going to write some code on your own that manages initial conditions rather than relying on LFilters, zero initial conditions. I want you to just write it out so you can just understand what makes it tick. And it'll be a little bit different than the way this one works, but you will come back to that. We've gone through frequency response for different types of filters. We kind of started the day off with reviewing through the moving average filter and this comb function response with the alias sync function. This is a section of the book. I'm not going to go into that. It's interesting, but it just relates steady state and how things eventually get up into steady state. And I think we saw that last week when I demoed some things with a sinusoid and a filter. Remember how we saw transient in the beginning, and then it becomes what you're used to seeing in the lab. If you're more interested in those ideas, though, we can jump back over to here. I'm not going to run them. I'm just going to use the table of contents. I got into frequency response, and I picked the first order difference equation. Plotted its frequency response. I guess since this was reevaluated, I have to reevaluate. Plotted the frequency response magnitude and phase. And then down here, I do the business of putting in a sinusoid and show the input and the output like we did last week. So that was embedded in this notebook. We played around in the notebook last week too and did something similar to this. So the next thing that I'll have to clean up after the break will be Fourier transforms of sequences and how Fourier transform of sequence gives us the spectrum of a sequence. Fourier transform of the impulse response gives you the frequency response. And then we can get into the theorems. And then one thing we're going to revisit again after I talk about the continuity and the convergence is we're going to visit the ideal low-pass filter. We talked about that briefly last week, but now we're going to actually say, okay, if we have this ideal low-pass response, because we now will have the Fourier transform and its inverse, so we can think about going backwards with the inverse Fourier transform, we're going to contemplate what it means to have the impulse response of the ideal low-pass filter, and then see how in DSP we can do some pretty cool things to get pretty close to the ideal low-pass filter. Because the ideal low-pass filter in the analog domain, you know, is non-causal, and it's just, you know, it's the brick wall filter. You can't get it exactly, but with DSP you can drive very close to it with code, whereas in the analog domain you have to build a really high order analog filter which can have a large component count. If it's done with active networks, it could become unstable. I mean, a lot of things happen in the analog world that the DSP world doesn't have happen. Is that reasonable? Now, let me just back that up, though, by saying in the analog world, it's just components I lay on the circuit board. They age, they have all these other bad things, but they're there, If it's a passive filter, it just sits there. I don't have to put power to it. It's not like it requires batteries or something. So there's a lot to be said about the old-fashioned, analog filters, the things that are still the bread and butter of radios and things. To get a DSP filter to really show its great performance, part of what you're going to be seeing in the lab, is because we have instantiated all this hardware to be an engine. So don't lose sight of that fact. Don't stand in front of your customer and say it's going to be great and it's going to be free and it's going to use no power. It's not true. It's not free. It doesn't use no power. And I guess if it's in a weapon system, a smart bomb that's being guided to its target, it gets blown up anyway. And I'm not sounding that that's a good thing, but I'm just thinking about what I keep reading in the news about what's going on over there in Russia and the Ukraine. It's not fun stuff, but it is kind of war and peace and all that other stuff. So our technology goes into that. So just like automobile electronics, we put a lot of systems in to hopefully survive a crash better. Crashes are unfortunately not unavoidable, but if we can minimize the impact and anything like that, we'll use our technology, and if it gets destroyed. I broke my collarbone riding my mountain bike. I had an accident. My head hit the ground really hard. I got a crack in my helmet like I'm supposed to get. It absorbed the shock. I walked away from that accident with a broken collarbone, but it could have been a lot worse. So in the helmet, what did I do with the helmet? Threw it away, because when it cracks like that, my brother, who's a big cyclist and has broken both of his collarbones, said, that helmet has served its purpose. It saved your skull, but you got to put a new one into service now, because and these things are making sense in terms of technology, right? That's what we do. So, okay, let's take the break. We'll now be coming back almost 10 till the hour. And if you got any questions, you can bring them up to me during the break time, and of course in the lab too afterwards. This is going to be a fun day in the lab. Fundamental tenet, though, of technology that you all have to abide by is everything that we do to help people can be turned around and misused in a bad way. And I think we just have to be cognizant of that fact and help as best as possible. The internet is such a good thing, but yet it's such a bad thing in a lot of ways too. And almost any technology seems like it gets spun around in a bad way. Okay, I won't tell any more stories, even though I'm tempted, because I'm dealing with things like this seemingly all the time just in my home life. So we were going to come back in and talk more about the Fourier transform as a tool. And I know some of you jumped into Fourier for one of the homework problems I just graded. And one person brought the Z transform in. I really did not want to see that this early. I mean, these are all tools, and you've seen them in 3205 and 2610, the other predecessor classes here at UCCS. We're just taking an upswing. We're going to hopefully at least take a look at the Z transform a little bit later today, and that's what the next homework assignment will be all covering from Chapter 3. So these are the these are our frequency domain equations that we have for the rest of the semester now, the DSP math as I call it. We've been through time domain, we've looked at signals, and we've looked at systems, we looked at linear constant coefficient difference equation systems. So now we move off into the frequency domain side of that, and we know that the Fourier transform, which is this one down here, is how we got h of e to the j omega, the frequency response of a linear time invariant system. So now we just generalize that and say it is a Fourier transform, whether it be a signal or whether it be an impulse response. And then the blue box up above is how you can synthesize a signal from a spectrum measure, namely the frequency spectrum. So the synthesis is the top equation and the analysis is the bottom equation. And more often than not, in a practical setting, we're using the bottom equation because we're analyzing. We have a signal, we capture it, we want to see what is the spectral content of that signal, and that is an interesting tool. The mathematics, though, of the synthesis is the power therein lies in the convolution theorem, which I mentioned last week and we see again today. If we want to get the output of a system as the convolution of the input and the impulse response, we can switch to the frequency domain, multiply the transforms, and then inverse transform. But under all circumstances, if we're going to hang out in the frequency domain is defined here, it's a continuous function of frequency. So in order to get back to the time domain, you have to go through an integral, which is not an easy thing to do in your hardware. So that's where the discrete time Fourier transform comes in. I'll just say also that this establishes what is known as the DTFT, discrete time Fourier transform. It'll be distinct from the DFT, which is just discrete Fourier transform, which involves a discrete base transform forward and reverse. This one is not that. This is the precise Fourier transform where you get a continuous function of frequency. We can evaluate the math at any frequency we want and have infinite resolution. So we have already seen in the case of the frequency response, x of e to the j omega is a periodic function that was talked about earlier. You can plug in on any 2 pi interval of the frequency domain and you get the same response repeating over and over again. We have real and imaginary parts. We have magnitude or amplitude spectrum and phase spectra. The phase spectra can be the principal value, which is the one that generally a computer tool gets you, and then we can have an unwrapped phase, which we'll talk about a little bit later, which is available in Python, and Julia I think has it too. I haven't really studied where I find it in Julia, but you were introduced to it, I think, at one point in MATLAB using a function called onwrap. Does that ring a bell? Remember using onwrap to unwrap phase? We'll get into that stuff later. The question at hand is proving that x of n can be synthesized from x of e to the j omega. In other words, if we go to the frequency domain, can we get back, and do we get back exactly? And that would be this proposal right here saying on the inside, we've done the Fourier transform of the sequence, and now we're going to turn around immediately and inverse transform to get back to the sequence domain. So the question here is this x hat of n the original sequence? So that's the statement right here. And it is. But the way to prove it quickly is to do something that mathematicians don't take lightly, and that would be taking this expression here and interchanging the order of the integration with the sum. In other words, doing the integration on the inside and the sum on the outside. And that requires some justification, which I'm going to mention in a moment. But right now, just go ahead and do that, interchange the order of the sum and the integration. So put the integration on the inside, and then you evaluate the integral on the inside, and it becomes a delta function. It becomes a delta sequence, delta of n minus m, because this integral, which you saw in other signals and systems classes, is the sinc function, And when the arguments of the sinc function are integers here and here, there's no in-between values. It's either you've got an integer argument, you have only an integer argument to the sinc function. So it very precisely produces a function that is either 0, or when n is equal to m, it's 1, because of the limiting value for the sinc function at argument 0. So we can plug that delta of n minus m back up in here. So this just gets thrown up into there, and now it sifts out in the sum. The delta function only turns on when m is equal to n, so that sum just reduces immediately down to x of n. Now, I didn't have to do that, and you can say, if you want, I didn't need to see that. I believed you in the first place. But there it is. There's the details. So now, what allows us to interchange the order of integration and summation? Why is that possible? And this is a detailed advanced calculus kind of area to dive into. I didn't get into that until I was working on my doctorate. So I took advanced calculus 2 semesters. It's also related to real analysis. You probably won't do that unless you get a doctorate, but you might have an advisor like I did that said you're going to take advanced calculus / real analysis and then do a little bit more. So it's called uniform convergence. So if we have a sum, an approximate to the Fourier analysis equation right here, rather than letting m be minus and plus infinity, the math approach would be to say, let's find this function for a finite number of terms and then see what happens as m becomes large. So uniform convergence says that the true function we're going to approach as m goes to infinity, that's this guy, and the approximate value for a finite m, that's going to become really, really small, and if the absolute value of that difference is less than or equal to epsilon for m greater than equal to n, where n is a function of epsilon, but not a function of omega, then we have what's called uniform convergence. And that's a math term, but put it in a practical setting, it's just saying it works. I mean, the error gets really small, and if I just keep bringing up m, it uniformly just comes right in there and locks onto the limiting value. And that's what the uniform convergence is. It's embedded in this idea right here that as long as I make m greater than some n, I can always make the absolute difference be less than epsilon. And you say 10 to the minus 3 for epsilon is not good enough, I want to go 10 to the minus 10th. I got you covered. I'll just make m larger, and it will make that difference, absolute difference, smaller, and it just keeps heading in the right direction. And for us, people that take calculus, we just want to know the limit as something gets large or something goes to 0. Does the limit exist, right? And that's what this is saying. It will exist because it's going to just shrink down tinier and tinier. A sufficient condition for absolute convergence is to say that the absolute sum of a signal x of n or impulse response h of n be less than infinity. Where have we seen that before? Linear time invariant systems. Remember, a requirement for stability was that the absolute sum of the impulse response would be less than infinity. I mean, I was grading those homework problems on Monday, and I was seeing your arguments about that, or lack of arguments, whatever the case may be. So this is the same condition, actually, for the existence of the Fourier transform. It says sufficient condition. If we can show this, then we've shown that it's absolutely summable and the Fourier transform exists. This also means that the Fourier transform converges uniformly to some continuous function of omega, which is what we're wanting for our DTFT. So this will come back a little bit later in chapter 3. We'll see it as a similar condition for the Z transform to exist in a certain region of the Z plane. We're going to want to have absolute summability. And then a little bit beyond that, and this happens in chapter 3, we'll see that the region of convergence in the Z plane is a region where there are no singularities. And then that eventually leads to the requirement that the region of convergence, if it includes the unit circle, says that the Fourier transform exists. And then that also will tell us that if it's a system, H of n, that the system is stable. So we're going to be moving in that direction, and it's pinned down on the one side by this result right here, which, you know, we've already seen this version of it for the impulse response. So I want you to kind of keep this in memory. I realize that the math part of it, of absolute convergence, is over the top, but this is still fundamental for what we're going to be moving on, and it becomes a fundamental result that is used all the way through the rest of the course. So actually my pen will continue to work. It's right there. A weaker form of convergence is mean squared convergence, where you're talking about the absolute sum squared less than infinity. And this leads to mean squared convergence, which is something you're familiar with from Fourier series from back in ECE 2610, where you're talking about how do you approximate a square wave with a finite number of sinusoids. That's the Fourier expansion formula, and you're used to the idea that a square wave using a finite number of terms in the Fourier series does not converge absolutely. It only converges in the mean square sense. So you always have that ringing on the top of the square wave when you only include a certain number of harmonics, and no matter how many terms you add on, it still has that ringing. So those types of waveforms are only convergent in the mean square sense. Just to tweak your memory and get some connection going, a sum like this, if I put 1 over n inside of here, remember from calculus, if you sum the harmonic series, it's divergent. It does not converge. Remember that? Whereas if you make it 1 over n squared, it does converge. So this is related to that particular example that would have been, I don't know, calculus 2 maybe. I mean, that's where they're seemingly in calculus, the way I look back at it, is they were trying to get your brain primed for things yet to come and make you start thinking that, what are these curiosity things? I mean, 1 over n is not good enough. 1 over n squared is good enough for being convergent. Okay, so now we can go ahead and use this immediately in considering the ideal low-pass filter. So the ideal low-pass filter has this as its frequency domain response. We established that in an earlier example. But now we want to take this into practice and say, this is our desire to come up with the ideal low-pass filter. Let's just go ahead and inverse Fourier transform, and that should tell us what the impulse response is of that filter. And very simply, it's a familiar integral from continuous time Fourier transforms from a previous course. It's just the sinc function, sine omega c n over pi n. And this is immediately what we were just talking about, this is an impulse response that is not absolutely summable because it is of the form of the harmonic series. It decays at a rate of 1 over n, not 1 over n squared. So the Fourier transform of this brick wall filter is not actually possible with convergence pointwise. It's only convergent in the mean square error sense. So pointwise, what I'm meaning is that it doesn't absolutely hit 1 in the passband. It's got that ripple in the passband. And it doesn't absolutely hit 0 in the stop band. It's got that ripple. And the ripple never goes away, even if we make m larger. It's always rippling in there. And you remember that as the Gibbs phenomena from Fourier series from a long time ago. So initially it's like, this is very depressing. I can't build an ideal brick wall filter. You're supposed to be kind of sad feeling right now because I just told that to you. But the good news is we can do a little bit of modifying and we can get very, very close to it. I'm going to come back to this with an example in Python, but another type of Fourier transform is where we have an impulse in the frequency domain, and because we're talking about a sequence, having a Fourier transform is always going to have a periodic spectrum. So if we have periodic impulses in the frequency domain, we have to have it at all multiples of 2 pi. In this particular case, if we have a single spike in the frequency domain, e to the j omega, so it's a spike, it's a delta function sitting here at omega naught. That inverse transforms back to a complex sinusoid if we allow what's called a Fourier transform in the limit. And you can put up as many delta functions in the frequency domain as you want. This would be like an idealized spectra of some signal, like maybe it's a radio signal, maybe it's a heartbeat signal or something that's got periodicity, so it's got harmonic components located with delta functions. And in particular, you can build up a cosine omega naught n by just putting down 2 delta functions. So these are the two deltas that you have to build a cosine, one at plus omega naught, the other one at minus omega naught, and then the periodicity just makes them run up and down the frequency axis. But generally in our modeling, we're generally thinking of the fundamental interval is minus pi to plus pi. So this is actually comforting. Even though it's a Fourier transform in the limit, it just says if you have an infinite cosine signal, it will have, as its Fourier transform in the limit, it will be delta functions that are just precisely at plus and minus omega naught. In a real system, it doesn't go on for infinity, so it's got a little bit of spectral blurring going on, or dispersion, and we're going to be looking at that in a bit. In terms of doing Fourier transforms, numerically we use the freq z function, and that is located in Python in the signal package of SciPy, so that's where we actually get freq z from. In Julia, I've written a function in my module called freq z, and it comes from the DSP package written by the Julia community, and I just simply rewrapped it to make it more convenient because it's seemingly harder to find. I'm not super happy with the way the Julia community is building out DSP stuff. It's kind of a hodgepodge of stuff, but I think Python probably started off similarly, and it got tighter as time went on. So Python is definitely very well organized at this point. So I just did some plotting with FreakZ in here, and there's not really anything too exciting about it. One of the things that I'll just point out is I always prefer to plot with the frequency axis being the normalized frequency omega over 2 pi. And in the book, sometimes this is denoted as lowercase f. It's got units of hertz per sample. So it's a normalized frequency. It's not frequency in hertz, it's frequency in hertz divided by the sampling rate, and we'll see that when we get to chapter 4. I just like this because I like having an axis that's got nice fractions on it rather than fractions of pi on it, which is kind of awkward to look at. But what's your preference? Do you like seeing fractions of pi? To me, it's just makes no sense. I want to think in terms of hertz, normalized hertz, rather than radians per sample. So I always do my plots that way. These are just taking some rectangular pulse shapes and doing them. So now we're going to go briefly look at symmetry properties and then get into some theorems. So the book spends a lot of time on symmetry properties, and symmetry properties are full up complex. So they look at conjugate symmetric and conjugate antisymmetric, and this is a little bit more robustness than what I care about right now in the class. So I'm just going to skip over the full up conjugate symmetric, conjugate antisymmetric. It seems like it shows up in a homework problem at some point. I don't think it's not in a homework problem right now, though, I don't think. No, I didn't give you any problem on this yet. So I'm just going to go down to the special case. Where we have just real signals. So a real signal is just conjugate symmetric. So it means its magnitude is an even function of frequency and its phase is an odd function of frequency. Furthermore, the next bullet down there, if a signal is even on the time axis or integer discrete axis, then its imaginary part is 0. If it's odd, then its real part is 0. These are the exact same properties you see in the continuous time domain. If you have a real signal, spectrum is magnitude is even, the phase is odd. The book has these tables, the full up symmetry conditions. If I do give you this homework problem, you utilize this in that problem. Okay. This example is one that I have in the Jupyter notebook already, but it's just looking at our signal, or it could be our system. Remember, it's a first order difference equation. The impulse response was a to the nu of n also for a causal first order LCCDE, just looking at playing around with this. So don't want to spend a lot of time on it, but I do want to show you the basics, which is right here, and that is that the geometric series wins the day again, and we're going to use geometric series sum formulas. So you look at that sum of this impulse response, it goes from 0 to infinity. You say, I can get that in closed form. I can get it in a simpler form. And you just simply recognize the fact that reliable Bluetooth, that's the ratio R in the geometric series sum formula. And even though it's complex, it doesn't matter, the sum formula still works. Remember when I did the back of the envelope calculation thing, I had a number in there, A. I didn't say whether it was real or imaginary, so here it's imaginary, it's complex. I mean, A e to the minus j omega raised to the nth power. I know that's just going to sum up to 1 over 1 minus the ratio, and there you have it. And then the convergence condition is that, magnitude of R has to be less than 1 for it to converge for the infinite geometric series. And so that throws the added requirement on here, and this will be stability later on, but this we know is stability if it's an impulse response. And for the spectrum to be bounded, this is also a requirement. So magnitude of A less than 1. So that's a single exponential, and then the spectrum can be expanded out into real part and imaginary part, or magnitude and phase. And I kind of go through all the gyrations there, just like I do that over here too. Somewhere in here I did that. Well, I did it up above here. There's the spectrum, and then I just wrote out a little bit of it in here. I'm kind of looking at the clock and looking at how I want to drive things here. So I just observe symmetry properties through here in those plots. And we can observe those when we look at some plots later. So now we're going to look at some theorems, though, the fundamental theorems, and then establishing the notation. So the script F, if you're writing this in LaTeX, it's \math \math cal, meaning calligraphy characters, and then put in braces. F will give you that script F. Probably didn't think calligraphy would ever get involved with an engineering course, but it's the way the fonts are notated, and it works in the notebooks that way. So x v to the j omega is F, or Ft. Sometimes I will say Ft, and then IFT down here to go back to the sequence domain, and then a double-ended arrow with a calligraphy F over the top of it means it's the Fourier transform pair to go back and forth with. So we have nice simple linearity result, which comes about from the properties of integrals, that you can break them apart and use and develop the linearity result for the Fourier transform pair. Time shift theorem used in the difference equation problems, what you have in the homework in particular. This is very powerful. It just says that if you shift a sequence, you end up pulling out a phase shift factor, which corresponds to the time delay in the frequency domain. So e to the minus j omega nd pops outside of the on-shifted transforms signal, x of e to the j omega. And an application of that would be, well, this is the proof of it. Well, frequency shift, time shift, never mind, frequency shift. Frequency shift is the dual where you're going to multiply times a complex sinusoid. And what that does, when you prove that out, it takes and shifts the spectrum. So in this case, let me get this down. As a result of multiplying by e to the j omega naught n, you shift the signal up in frequency or down depending upon the sign of omega naught. And this is utilized in software-defined radio a lot. I refer to this as spinning the signal. If you have a signal and you're going to multiply by an e to the j, you're actually spinning it around in the complex plane. So you're spinning it up in frequency, you're spinning it down in frequency. And if you're building a receiver, you generally are thinking about taking a high frequency signal and bringing it down to DC, or the baseband, and then work from it from there. So we'll see this in operation at various other points in the semester. Parseval's theorem is a handy calculation means where you can switch between time and frequency domain. We'll take advantage of this at various times. It just says that there's a preservation of energy in the frequency domain is energy in the time domain of a sequence. Now, just stop for a second. In the continuous time domain, the energy unit is what? Joules, right? What's the energy unit going to be here?
Joules per hertz.
Well, it doesn't have a dimension, actually. It's a dimensionless quantity, but we can work it into a true energy calculation. I just wanted to just stop for a second and, what would the units be? If X was a voltage, let's say, then it would be volts squared. So it's not, there's no seconds in there yet unless we put some equivalents in there. It's still called, the bottom line is we're calling it energy, although it's not joules. It's just like energy because it has the same type of calculation. So here's just the proof of that. Convolution theorem, powerful one, probably the most powerful at this point, convolving in the time domain or sequence domain, leads to the product of the Fourier transforms. So we use that one a lot. A new one, somewhat newer, is modulation or windowing theorem, and it's what happens when we're multiplying in the time domain, what happens in the frequency domain. So when we multiply a signal by W, and W is thought of as being a window, so we've got a signal that's rumbling along, multiply it by a window that will shape it and turn it off, let's say. Simplest window would be just a switch, or corresponding to the capture of a waveform from a receiver. And why does that make sense to us? We're listening, right? We're listening to signals maybe in an operation. We're going to capture something and then we're going to process it. So that's where the window comes in. We process it to see what the spectral content is, to see what the Doppler shift is on the signal we sent out and got echoed back to us, or what is the signal that we're seeing out there. So that's the windowing theorem. And the windowing theorem just moves the convolution into the frequency domain. See, in the convolution theorem, we've got convolution on the time domain, and we've got multiplication on the frequency domain. In the modulation theorem, we have multiplication in the time domain, and then here we have like a convolution. It's actually what's known as a periodic convolution, because we're just integrating over one period, because these are periodic spectral like functions. So it's like a convolution though in the frequency domain. But it's known in DSP also as the windowing theorem. So I want to show a little bit of those two before we leave today for sure. So what I also have in the notes here are very handy to have by your side when you work problems is transform theorems that we've just been through, and there's more on here than what we talked about. We only talked about a couple of these. Talked about that, and that. We didn't talk about 4 and 5. We talked about Parseval's theorem. We didn't talk about the generalized Parseval's theorem, but they're out there and we can make use of them. Some of these come back again in the Z transform and are more useful in the Z transform domain. Then we have transform pairs. So this thing will get to working. We've done those three already. This is I just say too easy. When you have a single point in a sequence, there's only one value in that sum of the Fourier, discrete time Fourier transform, you get one. So it's kind of obvious what that would be. And if you have a delta function that's delayed, you get the second one. If you take the delta and move it over by n naught, you get a complex phase shift factor just by delaying a signal. Others are a little bit more obscure. We've actually seen this one already. That's the ideal spectrum or low pass. This one I have a proof of in the appendix. This one is kind of funky because it has this that's present. You would expect only that first term, but that's because of the way the Fourier transform is defined, you get that too. And it has to do with the fact that U of n is not absolutely summable, right? If you try to sum it up, from a systems model, it's not a stable system. And if you look at it as a signal, it's not absolutely summable. So it doesn't really have a true Fourier transform because it has the delta functions in there. It has DC in it is what it's got. And I guess we've seen those as well. And this is our moving average, the sine mx over sine x. We saw that one already. So in terms of what transform theorems do, this is just an example about how you can get there from the theorem. So this is a real simple example. It just says you have a to the n times u of n minus 5. How would I approach that problem using a theorem? I could start from scratch, always can work from scratch, but do you want to reinvent the wheel all the time? Previously, when you've used transforms, it would be Laplace or Fourier in the continuous time domain. You find transform theorems in pairs are helpful to get there with more efficiency or more ease. So in this case, the approach I took was to bring out a to the 5 and then have this be heading towards the use of the delay theorem. So I have a to the n, so where n appears, it has to be consistent. So I have a to the n minus 5, u of n minus 5. So I can apply the delay theorem on that. And then I just use the a to the 5 that I factored out and leave it as a linearity property. So that just carries on through to the transform side. And then this is taking the delay property, the e to the minus j5 omega, from the n minus 5, and then I say the undelayed signal would be the Fourier transform of a to the n u of n. So when I put that together, I just get this. And if you were going backwards on this, you would do the same thing. You would home in on, that's a constant, that's a delay, and then you've got times 1. So you got 1 over 1 minus a e to the minus j omega, would be an a to the n. And then you have to just work the theorem on that accordingly. Okay, 6 minutes. This is the last example that's new, just so you can see. We talked about this example. But in terms of homework hints, just to make sure that you're good with this, does anybody have any more questions so I can back into what I want to do with the remaining time? This just said that if you need to get the Fourier transform of a difference equation, you just transform term by term using the delay theorem. Then you can form the ratio. If you want to go back to the impulse response and you're willing to tackle the use of partial fractions, you can get the impulse response from the Fourier transform. We'll see in the next chapter, though, that the Z transform is the best way of getting an impulse response from the transform domain or a step response. But right now, I'm kind of keeping you in a protected mode where I want you to appreciate the power of the classical solution technique and not just start using the full magic of transform theory. I want you to kind of grow into it and be respectful of it. There's an appendix here, and I'll maybe refer to these later. I don't really need to do them now, but I do want to do a little bit in Python and also talk about this example. But I'm giving you one last chance to ask me about anything else in the homework before I jump off and show you some interesting things. This example is an interesting example, windowed sinusoid spectrum. And I think well, I was going to talk about the low pass. I don't think I'm going to get a chance to do that. I'm going to talk about the windowing here first, spectral estimation and windowing. That's what I want to do. So this example, though, is a classical example. Put yourself in taking a measurement in the lab, or you're building up a system to receive some signals, maybe sonar signals, and wanting to know what's out there, what's in your capture. So we can't capture an infinite duration cosine wave. We only have so much processing power, so we capture n+1 samples in this case. So the dark stems are the ones that are in our capture window. We think of the sinusoid running for all time. We know it will have a spectrum, which is just the impulses at plus and minus omega naught, and then the sum here just extends it to the periodic extension of it. I can't make that go away, but you can just, if you just focus on what lies on the interval minus pi to plus pi, there's two spikes, minus omega naught, plus omega naught. To be thorough with the math, though, we have it picked up, plopped down all those times, and that's why it looks kind of messy. If we want to find the Fourier transform of that, though, we clearly have an example of a window. So we have x of n, the sinusoid sequence, then we have our window w sub n, multiplying them together. So if we want to get the spectrum of the signal that's following the windowing, we get the spectrum of the deltas, which is embedded inside of here. And then we're going to do the windowing theorem, so then we have to multiply times the Fourier transform of the rectangular window, which is going to be the sine mx over sine x function. And that's what the rest of this piece is in here. And then the amplitude's out in front. So that looks big and ugly, right? But we're only integrating from minus to plus pi, so we only need one delta function from this first term, the one that's going to be at plus omega naught, and then we're going to have another delta function at minus omega naught to hit this function in green at those respective frequencies, plus and minus omega naught. So we just get two terms popping out of this, and that is the theoretical spectrum with the impact of the windowing. And this introduces what's called spectral leakage. Here's just a plot in Python, but there's what the spectrum looks like. It's got blobs, spectral blobs at f naught or omega naught. Here I've got it divided by 2 pi, so plus and minus f naught is where these spectral blobs occur. And that's the result of the windowing. The windowing is creating what's called spectral leakage. It's dispersing the frequency content around the infinite duration cosine wave. And so if we look at spectral estimation with windowing, which I built into the notebook here, here's a theoretical spectrum. I just generated 1,000 samples of a cosine. It's still windowed, but I'm not zooming in on it, so it looks perfect. I have two spikes plus and minus omega naught, and then at 2 pi and minus 2 pi it's repeating. But now what I do down below here is I'm going to window it. So here I create the same signal. I create two sinusoids actually, create a window of 100 samples, and then also create a second type of window, but I multiply them together. Notice in these two lines of code, I'm windowing first with the rectangle window and then the Hanning window, which is a shaped window. Unfortunately, I talk about the windows up above, but I'm going to run this and I'm going to be out of time. So there's the signal creation and here's the plotting. So the rectangular window, if you look at it in a dB scale, which is what I've done here, I'm doing 20 log base 10 the magnitude. So this should say dB. Add that to my plot. The leakage rolls off very slowly with the rectangular window, and I can't really see the fact that I've got a weak sinusoid close by. In this plot up here, I've created a sinusoid at 1.5 times the frequency of the strong sinusoid, so I put in a weak sinusoid above it. When I use this Hanning window, it gives me the orange spectrum, and you can see that its side lobes roll off a lot faster, and I'm able to resolve some information from this weak signal next to it. And this could be useful in a radar just receiver application. You don't want the strong signal to swamp out the weak signal. You want to be able to discern it. So what we're doing is we're applying an advanced technique to window other than the rectangular window. And what do the windows look like? So I've got that up here. Let's see, I think I've got two window functions in here if I'm not mistaken. Nope. These are sync functions, so that was the ideal low pass example. Got to get down here. Here I'm creating the two window functions. Boxcar, which is rectangular, Hanning, and now I'll plot rectangular in the time domain, Hanning in the time domain. So we see we're tapering the response to keep it from having such a high side lobe level. So I look at that action in the frequency domain, and we're seeing why we get better performance with the Hanning window. We get a wider main lobe, but we get the side lobe leakage to go away. I'll say more about that next week, but this is just a nice application area where you can decide to use a window function. And digital oscilloscopes that we have in the labs have the ability to select different windows to see signals in the frequency domain better than without the window. You'd think, give me all the data and not tapering it would be a good deal, but this picture just is to try to illustrate the fact that the weak signal is getting cluttered over by the strong signal. Do you want that to happen? Do you want to miss a radar? Like it would be like in a collision radar system, a reflection from an oncoming car or some obstacle might be diffused by the car right in front of you that's at a constant velocity or something. I don't know, I'm just kind of dreaming about how you can process intelligently. We are out of time now. For those of you in the lab, I'm going to be moving up to the lab and getting the boards handed out.